Hi everybody. I'm going to continue with our, what I'm calling our meta-theoretical interlude. In the last lecture, I talked about the things that we're going to be proving during this interlude. This is the interlude between our work in sentential logic, and after we finish this, we're going to start taking a look at what's called predicate logic. So that's something to look forward to next week. So what I said is that in this interlude, we're going to do two things. The first thing that we're going to do is to show that the language SL is an adequate language for its purposes, and that's what I'm going to do in this lecture. And the second thing we're going to do is to show that the tree method, the truth tree method, is an adequate method for testing for the validity of arguments in SL. That is, we're going to show that if an argument is valid, the truth tree method is going to give us the answer yes to the question, is it valid? And if the method does give the answer yes to that question, then the argument is indeed valid. Okay, and for that, I'm going to be posting a handout, which I have not posted yet because we haven't gotten to it yet. Okay, so the first thing we're going to do is we're going to talk about the adequacy of the language SL. And this is the only part of chapter 6 that we're going to be talking about, and this is called, another way to talk about this, and I think the book calls it this, is to talk about the truth functional completeness of the language SL. And I think it's in section 6.2 of the text. And so you don't have to look at any other part of chapter 6. In fact, if you do, it'll be kind of confusing because it talks about the adequacy of a method that's presented in chapter 5, which we're not doing. Okay, so what is this about? We want to be assured that the language SL is capable of representing all of the different ways in which sentences can be built up from other sentences by truth functional means. Because we want SL to be adequate for all of truth functional logic. So remember that we say that a sentence, or rather a connective, is truth functional if and only if it's used to generate a compound sentence from one or more simpler sentences, so the value of the compound, the truth value of the compound, is wholly determined by, is a function of the truth values of the components. And we talked about how our 5 connectives have this property of being truth functional, and we looked at a number of other connectives in English that do not have the property of being truth functional. Okay, so how can we show that there are no truth functional compound sentences that we can't represent in SL? That is, that every single truth functional compound sentence can be represented in the language SL. Well, we can't just look at a whole bunch of really complicated sentences in English and say, oh yeah, see, I can symbolize that one, I can symbolize that one, and that one, and that one in SL. We need to show that all of the possible ways of building up sentences from simpler sentences by means of truth functional connectives will yield sentences that can be symbolized in SL. And there are an infinite number of them. There are an infinite number of such sentences, which is why we can't just sort of look at a whole bunch and translate them and then convince ourselves, oh, see? Because we can't look at all of them. Okay, so the first step I want to take is to take a look. We're going to be thinking about the connectives as functions. So, we've been talking about truth functional logic. We're going to think of the connectives as functions. That is, we're going to think of them as being what we're going to call truth functions. And you guys, you learned about functions at some point in high school mathematics. So for instance, the plus function. A function takes arguments and yields values. So the plus function, when applied to, say, the arguments 1 and 2, yields the value 3, right? Or the times function, when applied to 2 and 3, yields the value 6. Okay, so you know what a function is. It takes arguments, it yields values. We're going to be thinking of our connectives as being functions, truth functions, and what they take as arguments is truth values, and they yield truth values as values. So these arithmetic functions take numbers as arguments and yield numbers as values, but truth functions are going to take truth values as arguments, and they're going to yield truth values as values. Okay, so the characteristic truth tables for the connectives that are part of our language SL defined the truth functions, right? So each truth function is expressed in SL by any sentence whose truth table contains in the column under the main connective exactly the column of T's and F's that occur on the right-hand side of the characteristic truth table for the truth function in question. So for instance, every single sentence of the form not P, so P being a meta variable, every single sentence of the form not P is going to express the negation truth function. So for instance, not A expresses the negation truth function, not A, horseshoe, B, and C. So the main connective there in each of these is the negation. So each of these is going to be a sentence that expresses the truth function negation, because under you're going to have just what you would expect under the main connective. You're going to have the opposite of whatever truth value you have for the sentence that's negated. All right, so we want to convince ourselves that for each truth function, for every single truth function, and we're going to have to think about how many of them are there. Are there just 5, or are there more than 5? But for every single truth function, there's at least one sentence of SL that expresses that truth function. And what do I mean by that? Again, a truth function is going to be expressed by in SL, by a sentence of SL, by any sentence whose truth table is going to have in the column under the main connective exactly the column of T's and F's that occur under the main connective of the characteristic truth table of the truth function in question. Okay, so again, we want to convince ourselves that for each truth function, and we'll talk about how many there are, there's at least one sentence of SL that expresses that truth function. Okay, so now, how many truth functions are there? So you might say, well, there are 5 of them, right? There's the one where you apply negation to true and it yields false, and you apply negation to false and it yields true. And then there's the one where you apply the ampersand to true and it yields true. You apply ampersand to true and false, it yields, oops, I meant to write down T and not F there, sorry about that. It yields true, but when applied to true and false, it yields false, etc. Okay? So, we certainly, there are 5. There are at least 5 truth functions. One corresponding to each of the 5 connectives that we have in our language. But are there more than that? I'm speaking slowly because I want you to be thinking about this before I sort of start giving the answer. Well, we can represent a truth function by means of a table such as this. So Here's an example. So this is the truth. This is going to represent the truth function that we're calling tilde or negation. We have true, false, and we have. So these are this is the argument of the function, and this is the value that the function yields when applied to the argument. So we call this negation. This is a truth function of one argument. It's a one argument truth function. Are there any others? Are there any other one argument truth functions? Well, maybe not one that's particularly handy to us, because one of our interests is in using SL to capture the logical structure of sentences in English. And the tilde was very handy because it captures basically what we mean by the word not, or it is not the case that. But are there, I'm asking you to think a little more abstractly now, are there any other one argument truth functions? Well, there's this one. How about the one that takes as argument true and yields true, and takes as argument false and yields the value false? Well, that's a truth function, right? I mean, it's not one that's going to be particularly helpful to us in our general project here, but certainly that's a truth function. And how about the one that takes true to true and false to true? No matter what argument you feed it, it gives the value true. Well, that's a well-defined truth function. And how about the one that no matter what argument you feed it, it yields the value false? Well, that's another one, isn't it? So far we've got 1, 2, 3, 4 truth functions. Because look, a truth function is just sort of defining, you know, when you feed it an argument, what does it yield? So here are 4 distinct truth functions that take one argument. So now the question of, you know, how many truth functions are there? Well, it looks like there are a lot. There are going to be a lot more than 5. Now, if you think about truth functions that take 2 arguments, we've looked, for instance, at this one. We call this conjunction, right? And we've looked at this one. See, I'm representing the truth function by means of this table, right? We've looked at this one. We call this disjunction. We've looked at this one. We called this one conditional. And we've also looked at this one. It yields true when the arguments are of the same, and it yields false otherwise, and we called that the biconditional. Okay, so there are at least 4 truth functions that take 2 arguments. Are there more? Yeah, there are a bunch more, right? Because, I mean, thinking about what we did when we were thinking about one argument truth functions, you know, we could have the one that yields true no matter what pair of truth values you feed it, or yields false no matter what pair of truth values you feed it, and so on. And so we're very familiar with these 4 truth functions of 2 arguments, but there are actually 12 more of them. There are 16 truth functions of 2 arguments. And if you've got nothing else to do today, you might see whether you can figure out what they all are. there's 16 truth functions of 2 arguments. In fact, okay, so now we're getting even more abstract. How did I get 16? Well, they're going to be 2 to the n truth functions where n equals the number of arguments of that function. That the function takes. Oh, wait a minute. The number of arguments that the function takes. So we've only looked at one place truth functions, negation, and, well, 4, two argument truth functions. What is she talking about where you might have, is it possible that you have a truth function that takes more than 2 arguments? Sure. So here's a table where this actually gives you a truth function that has 3 arguments. Say when you feed it true, 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 it gives you true. When you feed it true, true, false, it gives you false. And here it gives you true. You feed it false, true, true, it gives you false, false, true, false. Okay, so this table defines a truth function, right? It tells you precisely what the function is. It tells you if you feed it the value is false, 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 it yields false. If you feed it the value is false, false, true, it yields false. If you feed it the value true, false, false, it yields true, and so on. So this is a 3-argument truth function. And they're going to be 2 to the 8. What is that? I don't know. Somebody figure it out. Truth functions. Is that 100 and... I don't know what it is. 100, whatever it is. They're going to be 2 to the 8 truth functions of 3 arguments. Oh, wait a minute. There's nothing to rule out the possibility of having a truth function that takes 4 arguments or 5 arguments or 6 arguments and so on. And so, again, they're going to be 2 to the n truth functions where n is the number of arguments that the function takes. So it looks as if, I hope you're seeing, that there are an infinite number of truth functions. We're really familiar with 5 of them because they're handy for us for a variety of reasons. But there's actually, theoretically, there's an infinite number of truth functions. Okay, whoa. So what is it that we set out to do? We want to show, stepping back again, we want to show that our language SL is capable of representing all of the ways in which sentences can be built up from other sentences by truth functional means. We want SL to be adequate for all of truth functional logic, not just the little part of it that we've looked at that's handy for us in our project of figuring out what a good argument is, coming up with a rigorous standard, coming up with a method for testing to see whether an argument meets that standard, and so on. But theoretically, there are an infinite number of truth functions. And so we need to show that given any truth function at all that takes a finite number of arguments, but there are an infinite number of them, given any truth function at all that has finite number of arguments, there's at least one sentence of SL that expresses that truth function. And how are we going to do that? Well, this proof is done in detail in the text. The claim is given a name. It's called meta-theorem. Meta-theorem, that's a good word, right? Meta-theorem 2.6.1. Okay. Meta theorem. You guys know what a theorem is from high school geometry. It's just something that's true that you can prove. And you know what meta means, beyond. So this is it's a meta-theoretical truth that we're going to show, theorem that we're going to prove. I'm going to sketch the proof. I'm not going to do this proof in detail. But the meta theorem, the claim is this, that every truth function, and there are an infinite number of them. I hope I've convinced you of that, right? There's an infinite number of truth functions. Are they all useful? No. To us, no. But theoretically, there are an infinite number of truth functions. Every single truth function can be expressed by a sentence of SL. We haven't changed our language, SL. SL still has just these 5 connectives and the sentence letters and the left and right parentheses. This is it. But every single truth function, and as we've seen, there are an infinite number of them, can be expressed by a sentence of SL that contains just the connectives not, or, and. Okay, this is what the book proves. I don't know what page, but it's Meta Theorem 2.6.1 in section 2.6 of the text. That no matter what truth function you've got, and what we've seen is that if truth function can be given by means of a table such as this, where you have to the left of your vertical line the arguments that you're feeding the function, and to the right of the vertical line you have the value that the function yields or spits out when it's fed those arguments, okay? So given any truth function at all, no matter how many arguments it might have, we want to show that every truth function can be expressed by a sentence of SL that contains just the connectives not, and or. And what does it mean again? I talked about this a moment ago. What does it mean again for a sentence of SL to express a truth function? That under the main connective of the sentence, you will have just the column of truth values that you have in the table that gives the truth function. Okay, so as I said, I'm not going to do this proof in detail, but I want to give you a sense of the proof. Because as I said in the previous lecture, one of my interests this semester is exposing you to as many different ways of proving things as we can within reason this semester. And this is a really interesting proof because it's what's called a constructive proof. That is, the proof of this meta theorem not only shows that this claim is true, but it actually tells you how to construct the sentence in question. It gives you a recipe for doing it. So it's called a constructive proof because it gives you basically instructions for constructing just the sentence that we're saying exists. Okay, and how does this work? So the connectives of a language. Let me go back. Remember at the very beginning of the lecture, I said that we were going to be showing what logicians call the truth functional completeness of SL. And what did I mean by that? The connectives of a language in which every truth function can be expressed form a truth functionally complete set of connectives. So what we're going to show is that the set of connectives, not, and or, is a truth functionally complete set. That is, that we can express all the truth functions using just those connectives. Okay. So how are we going to do this? So when I say it's a constructive proof, basically this proof is giving us what's called an algorithm. And this is a word that you hear a lot more now than you used to. It gives you an algorithm for constructing the sentence. What is an algorithm? It's kind of a recipe. It's detailed instructions for doing what we're showing here. We can do. So we're going to show that our set of connectives is complete, is truth functionally complete, by constructing an algorithm, this recipe, this mechanical procedure for constructing the sentence. So what we're going to show is that given any truth table like this, I'm going to call this a truth schema. Whoops, spelled schema wrong. Given any truth schema, see this, like these tables that represent truth functions, these are all truth schemas, these tables. So we can think actually of our characteristic truth tables in a way as being truth schemas. Given any truth schema, this algorithm that we're given is going to tell us how to construct a sentence of SL that uses just these three connectives that expresses the truth function that's specified by that schema. Okay, so just to make sure that we understand the language that I'm using. This is a truth schema that specifies, or this is a truth schema that gives us a certain truth function. And the function is the one that takes, these arguments and gives us these values. All right. So again, given any truth schema, these tables, this algorithm is going to tell us how to construct a sentence of SL that uses just those three connectives that expresses the truth function that the schema specifies. And the idea is pretty simple. The idea is that given any truth schema, given any one of these tables, we look along the rows and we see where the value is true. So for instance, let's start off with a 2-argument truth function that we can specify by means of this truth schema. So remember, we have to the left of our vertical line the arguments that the function takes, and to the right of the vertical line we have the value that the function gives us when applied to those arguments. So this is a truth function that yields true just when both arguments are false, and otherwise it yields the value false. So we're going to sort of start in alphabetical order, and we're going to put at the top of each column to the left of that vertical line a letter. We're going to start with A and then B. There are only 2 here. So we're going to think of the first column as A, and think of the second column as B. And now we're going to look at the case. In this case, there's only one instance where the function yields the value true, and it's when A and B, or both arguments, are false. And so we can see, I think, without any difficulty, that the sentence not A and not B is going to represent this truth function, right? Because if we were to do a truth table for this sentence, I'll write it down over here. I'll do another one. True, true, false, false, true, false, true, false. Let me just very quickly do the truth table for not A and not B. I get false, false, true, true. I'm just flipping A, and then false, true for not B. And then that's going to be false, 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 true. And so, not surprisingly, I get precisely the column of trues and false under not A and not B that I had here in this schema that specified the truth function that gives you true just when applied to false and false. Now, how did I cook that up? How did I cook up not A and not B? I applied the algorithm. So I'm going to give you a sense of what this algorithm is by looking at examples. But basically what the algorithm tells you is that you look at the truth schema, you head each column to the right of to the left of the vertical line, sort of starting alphabetically with A with a capital letter. So A, B, C. Here we only have A and B. You look at the row or rows where the function yields the value true, and you see that in this case it was just this row, and that's when A is false, in other words, not A is true, and B is false, in other words, not B is true, and I can join them. And so not surprisingly, it gives us this sentence yields, or rather expresses, the truth function that's represented by this schema. Okay, let's do another example. I'm going to do one that's I'll do one that has three, a truth function that takes three arguments. Okay? So first I'm going to set up the schema that specifies the truth function. It's going to have 8 rows, because there are 3 arguments. And let's say that this truth function yields the value true just when it's fed true, 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 or false, 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 and otherwise it yields the value false. So there are 3. No, let's make it this one too. So it's true here. It's true when it's fed false, true, false, and it's true when it's fed false, 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 and otherwise it's false. So this is a schema. This is a truth schema that specifies a truth function. This particular truth function takes 3 arguments. Okay, and now we're going to apply the algorithm, which gives us a recipe for detailed instructions, a mechanical procedure for constructing a sentence of SL that expresses this truth function. That is, under the main connective of the sentence that we're going to construct, we're going to have precisely this column of truth values. And the way that we do that is, the first thing we do is we label our columns starting with A. So we have A, B, and C. Then we identify the cases when the function, when applied to the arguments, yields the value true. And in this case, there are 3. When A, B, and C are all true, when A is false, B is true, and C is false, and when A, B, and C are all false. Okay? So these are the only 3 ways in which the function yields the value true. So now what we're going to do is we're going to look at these 3 rows, and so the top row tells us that when A is true, and B is true, and C is true, it yields the value true. And I need to put a set of parentheses in there because of our syntax, that a conjunction only has 2 conjuncts. And now we're going to look at this one, and this tells us that when A is false, in other words, when not A is true, and B is true, and C is false, in other words, when not C is true, and again, I need a set of parentheses there, it yields the value true. And then finally, when they're all false, in other words, when the negations are all true, not A and not B and not C, and it doesn't matter where I put the parentheses, and I'll put them in there, that these are the 3 cases where the function yields the value true. Okay, so now what do I do? How am I going to get one sentence of SL that expresses this truth function? Well, what I'm going to do is I'm just going to disjoin these. I put that or that or that. And if I were to do and I need another set of parentheses here because of our syntax, but if I were to do a truth table for A and B and C, which captures this case, or not A and B and not C, or not A and not B and not C, then under the main connective, which is this in the way that I've constructed the sentence, remember, we have to put in these extra parentheses here because in our language, a disjunction has exactly two disjuncts and a conjunction has exactly two conjuncts. It doesn't really matter where we put the parentheses, we put them there. So if I were to do a truth table where I'd have 8 rows and I'd have, the truth values would look just like this, only here I would put this sentence. Under the main connective, I would have precisely this column of truth values. And that's not surprising because what I'm doing is I'm saying, well, it could be this set of arguments that I'm feeding it, or it could be this set of arguments, or it could be this set of arguments. And that's why we're disjoining these 3 possibilities. So this gives you the idea that I hope you're starting to see how this algorithm works, that you look at the truth schema, these tables, you label the columns A, B, C, D, whatever, however many you've got. You look at the rows where the function yields the value true. You come up with a conjunction to represent those cases, as we did here and as we did here. There was only one case here. And then you disjoin those possibilities, and the result is actually going to be a sentence that expresses this truth function. Is it going to be the most elegant sentence? Well, no, absolutely not. You're kind of doing it by brute force, but it's a way you're guaranteed that no matter what truth function you've got that's specified by the appropriate truth schema, you can apply this algorithm, you can apply this recipe, and out will pop, albeit it might be rather long, out will pop a sentence, a well-formed sentence of SL that expresses that truth function, that is under the main connective of the sentence that you've got. You're going to have precisely the column of T's and F's that you have in the truth schema that express that truth function. So that's kind of cool. We've done it. I mean, this is kind of a sketch of the proof. The proof in the book is actually by mathematical induction, because we have to show that this is true for an infinite set of truth functions. But this is basically the idea. The proof gives you this algorithm and then shows that the algorithm actually works. Maybe some of you are thinking to yourselves, hey, wait a minute. What if I've got a truth function and it never yields the value, it never yields the value true, just to kind of be complete here, which is possible, right? So you might have, say, a 2-argument truth function that's specified by this schema, but it always yields the value false, right? So there's always going to, no matter how many arguments you have, you're always going to have a truth function where the function yields the value false when applied to any set of arguments at all. What do you do there? How do you apply the algorithm, since there's no case where there's no row where you have a true on the right-hand side of the vertical line? Well, I mean, you could, what the book tells you is that, again, you label you label this A and you label this B, and you just have A and B and not the conjunction of A and B. But basically, any truth functionally false sentence would do the job because it's going to have false under the main connect. You have false all the way down under the main connective. You just need a sentence that's got the appropriate number of arguments, so to speak, that are here kind of represented by the atomic sentence letters. So that's the algorithm. The algorithm is an important part of this constructive proof. the proof is of this meta theorem that no matter what truth function you're given, and we've seen that surprisingly perhaps there are an infinite number of them, of which, you know, we have particular interest in 5, but no matter what truth function you're given, that you can specify by means of a truth schema, these tables, every single truth function can be expressed by a sentence of SL that uses just not, and or, because the algorithm, as you see, you're only going to end up with sentences that use not, and or. Okay, so that's pretty cool. That's kind of interesting. So as I said, during this interlude here between chapters 4 and 7, I'm proving stuff about the work that we did in chapters 1 through 4. So what we've just done in this lecture is we've shown that shown the truth functional completeness of the language SL. That is, we've shown that no matter what truth function you've got, we can find a sentence of SL that expresses that truth function. So the language SL is capable of representing all the ways in which sentences can be built up from other sentences by truth functional means. It's adequate for all of truth functional logic, not just what we've been looking at, the logic of sentential logic. I mean, the language that we've looked at with the five connectives that we've been focusing on. Okay, so I'm going to stop here. I'm going to be posting later on or tomorrow. There's going to be a handout, and I'll put it into the files section, and I'll write you a note. But it's going to be called the adequacy of the tree method for SL. And that's another proof that's done by mathematical induction. And I'm actually going to go through the details for at least part of that proof by mathematical induction, because I think it's really interesting. It's good for you to at least follow along with this proof. As I said, I'm not going to ask you to reproduce it. I'm not going to ask you to prove anything by mathematical induction. As far as what I've just did today, I would really like you to understand what the algorithm is and how to apply it. But certainly I didn't go through the details of the proof by mathematical induction, but I would like you to have a sense of what it is that I've done in this lecture, what we mean by a constructive proof, and how to apply the algorithm that we just talked about. Okay, so I'm going to stop here. Bye for now.